So far in this tutorial, we have looked at various metrics that help data scientists to understand the anomalies, inconsistencies, and other attributes of the data and perform appropriate remediations in order to get a baseline data set for downstream analytics or machine learning tasks. In this concluding part of the tutorial, we will review the importance of human intervention in this workflow and discuss how subject matter experts can validate the recommendations provided by various quality metrics and how their feedback can be incorporated in order to make the data quality pipeline stronger and more reliable. Eventually, we will look at ways to streamline and formalize this human input in order to improve productivity and reuse. Human input occurs at various stages in the AI pipeline, and in the context of this tutorial, we will focus on the relevance and importance of human involvement within the data quality analysis or preparation phase. Putting humans in the decision loop ensures that data that enters an ML pipeline is of good quality and brings confidence in the overall proposed solution. A continuous feedback loop with humans also adds to the robustness and reliability of AI models. In this figure, we can see how various data workers, like data stewards, subject matter experts, and data scientists, are involved at various stages in the data ingestion and processing pipeline. Each may have different roles with respect to the kind of input they provide. A data steward may be concerned with the bias present in the data, adherence to business constraints, acceptable parameters and ranges for attributes, and also monitoring of lineage. An SME's role could be to validate the quality of annotation, identify label noise, review the various recommendations, and also offer remedial actions to remove these anomalies. Similarly, a data scientist may explore the statistical properties of data and look at other dimensions of quality like presence of outliers, class imbalance, missing values, and so on. However, this involvement of various stakeholders in current practice occurs in an ad hoc manner, often involving trial and error based iterative workflows. This reduces the scientific rigor of this exercise and also results in loss of productivity as expert human knowledge remains tacit and non transferable. Therefore, an essential step to make scalable and principled solutions is finding the right balance between automation and human involvement, with human involvement being used strategically for verification and approval of automatic decisions. The human roles need to work collaboratively in a streamlined manner. The data operations that typically occur as part of the data quality assessment include preparation, integration, cleaning, curation, transformation, and manipulation of data. Now, each of these operations involve use of specialized algorithms and can be really hard to navigate through the host of operations and their optimal sequence for an end user. There is also a probability of developing an affinity to a favorite method that may not, in fact, be optimal. So, in addition to being iterative, the nature of these operations is also ad hoc and often based on trial and error. Fortunately, there have been efforts to make this task easier with tools like Trifactor, OpenRefine, and Wrangler that offer interactive GUIs to enable even non technical users to perform various data wrangling operations. But several open issues still remain. So, for example, in the absence of a standardized objective measurement, how would you determine that the data is clean enough? One way is to give a quality score as an indicator of this information so that users can actually benchmark changes in quality. Secondly, how do you delegate and allocate tasks across various data workers without affecting the workflow? Similarly, how do we make sure that human input is retained as knowledge that can be transferred and applied to a similar context? This implies giving not just a statistical perspective to the humans in the loop, but also taking human factors into account in order to optimize both productivity as well as performance. Let us look at two examples from our toolkit that were discussed earlier and examine the role of human input in the workflow in order to understand the requirement for a tighter coupling between all stakeholders with a special focus on usability. Consider the remediation of label noise present in a structured dataset. Now, the first step would be to identify the noisy samples in a data, and this involves checking the target columns or attributes in order to detect noisy labels. And a data scientist, for example, who is interested in pre-processing the data for model building, may be interested in looking at whether all the feature attributes are consistent with respect to the labels supplied. The second step would be to give a visual preview of this noisy data and also show the predicted labels that the algorithm is supplying. Now, if the number of records is pretty high, then this may involve an ML engineer to devise an effective sampling algorithm so that you're able to subsample problematic data records and show it to the user in some logical batches, and then, for the next stage of taking the human input. Taking the remediation input may involve a domain expert where their input is required to verify and assess the metric output, which is the noisy labels are in fact noisy or not, and whether the predicted labels are accurate or not. And the human in the loop here, actually reviews, corrects, and approves all the recommendations that are supplied by the algorithm. And a final stage, which is a best practice, could be to learn these operations for future recommendations so that future effort by the humans is actually reduced and some transfer of knowledge occurs. So, for example, in this scenario, can we use better predictions? Can we predict user actions? Or even recommend strategies to correct data. Let's consider another example of detecting heterogeneity in a data column. The data homogeneity metric detects heterogeneous samples from attributes of a given data set and identifies the distinct patterns in data. Now, this metric can be potentially used by a data steward or even a data scientist to detect the anomalies and inconsistencies in data formats. For example, the target column in the adult data set has entries like less than equal to 50K, less than equal to 50K followed by a dot, greater than 50K, and greater than 50K followed by a dot. It gives a false impression of this being a 4-class problem instead of actually in fact being only a 2-class problem. The other example could be where terms like male and capital M or female and capital F being used for the same entity, which may also change the nature of the data. The second step is giving a visual preview of the problematic data. And again, if the number of such records is very high, then a sampling algorithm is required to take a representative subset of erroneous records. One may also give an explanation of why the data has been highlighted as being problematic by showing the distinct formats before asking for correction or verification. In the next stage, the visual preview is given to a subject matter expert for review and expected transformation rules, which are then finally taken back by the data scientist for propagation of the required changes. The transformation rules could be to rectify the heterogeneous data formats, specify certain rules, or even retain the data as is. Again, the final step would be to document and preserve these operations for future recommendations and suggest possible remediations in future. And it is quite evident that these workflows are customized per problem or enterprise, and the shared collaborative system that could streamline all these activities is actually missing. Even these seemingly simple problems require interaction between various data workers, and a mixed initiative interaction that combines all these efforts and inputs is actually the need of the hour. So, if we look at ways to optimize human intervention, we will be able to focus efforts towards building of shared collaborative workspaces to streamline and regulate human in the loop involvement. We should aim to reduce the amount of information to be reviewed by humans, reduce the manual effort to apply corrections, and automate as much as possible the rules or heuristics for remedial actions. Some principles or things to keep in mind to achieve these are: providing an easy to use specification interface. For example, a graphical interface rather than use of complex grammars or regular expressions, giving a visual preview of the relevant problematic data chunks, a minimum latency in order for users to see the effect of their transformations very quickly, establishing a clear lineage where we record the changes that have been done to the data and by whom, to enable the assessment of various data operations by using default machine learning models so that users can see the impact of changes that are done as part of the remediations. Data versioning to enable experiments for trial and testing, for example, the ability to undo changes and not affect the other operations that may have been done. And finally, using a streamlined collaboration to using task lists and shared data cleaning pipelines to streamline the whole process. Uh, to sum up, we ought to focus on factors like usability, explainability, visualization, and appropriate documentation in order to streamline and regulate the various data operations. Finally, to conclude this tutorial, I would reiterate the fact that data scientists spend a significant amount of time in addressing data cleaning issues and ensuring that input data is of adequate quality for downstream machine learning tasks. This is because the performance of any machine learning task is upbounded by the quality of training data. In this tutorial, we have emphasized on the importance of data quality and its associated challenges. We have described methods for analyzing the readiness of input data for ML tasks through multiple standardized quality metrics and also proposed corresponding remediations. The key takeaways from this tutorial are the following. Addressing of data quality issues before it enters an ML pipeline is actually allows reducing model building efforts and turnaround times. Measuring the data quality in a systematic and objective manner can improve its reliability and permit informed reuse. There are various metrics to quantify the data issues based on whether the data is structured or unstructured. There are various data workers or personas that are involved in the data quality assessment pipeline depending on the level and type of human intervention required. And finally, streamlining the collaboration between the usage of these standardized metrics and human in the loop inputs can actually serve as a powerful framework to integrate and optimize the data quality assessment process. Thank you all for participating in this tutorial. We take this opportunity to invite collaboration on this research agenda. So do get in touch with your ideas and inquiries. We do look forward to hearing back from you all. Thank you once again.